properties of waves. So the first one that you look at, or we looked at, was refraction. So it's the bouncing off of a wave when it encounters, you can say either encounters or when it hits a reflecting surface. And basically what you observed in this one was the idea that if this is a wave and this is a reflecting surface like a mirror, and this is the angle of incidence, this being the normal. Hope you remember that the normal is always perpendicular to the reflecting surface. So this being the angle of incidence, it will be reflected off the surface at an angle called the angle of reflection. And these two angles, I is the angle of incidence and R is the angle of reflection. Now, one of the most important things to remember is that the angle of incidence is equal to the angle of reflection. And this one, we call it the basic law of refraction. It's the basic law of reflection. All right? So that is the first property of waves that we must have covered. That is refraction. All right? So points to remember is that this is known as the incident ray. This is called the reflected ray. So I is the angle of incidence and R is the angle of refraction. The angle of incidence is always between the incident ray and the normal line. The normal is always perpendicular to the reflecting surface. And then we have R is the angle of reflection. Again, it's between the normal line and the reflected ray. And then finally we have what we call the basic law of, this is the basic law of refraction. And this basic law of refraction is simply saying the angle of incidence is equal to the angle of reflection. That's it. That's the first property of waves. The second one, the second property, we call it what? Refraction. It is the not speed of light, it is the bending of light. Bending of light. When it travels between mediums of different densities. And then we said the speed of the wave changes, and also what? And also the wavelengths. And also the wavelengths change. So during refraction, two things happen. That is, the speed of the wave will change. That is, the speed of the wave will change, and also the wavelength changes. Okay? And this is what causes the changing of direction that we are calling the bending of light. That is during refraction. Last time we said, if a ray of light passes through the normal, like if this is the reflecting surface, and we have the normal here, if you bring a laser torch through this line, so that the ray of light passes through the normal, does it undergo refraction? Will this ray undergo refraction? It won't. So it just perpetuates in this other medium through the same line. So it doesn't undergo refraction. However, there are some things that happens, two of them. These two things will still happen. So if this is air and this is water medium, and this is the wavelength, we just show the wavelengths using the wavefronts. So once it comes to this other medium, what will happen? The wavelengths decreases. So this is the wavelength too. So the wavelength will decrease. That is given. Okay? And there's something we call the wave equation. Wave equation. Wave equation. Wave speed is equals to wavelength times frequency. It's the wave equation. The wave equation, that's the one. And the wave equation, we can also use symbols. Acceptable, V is wavelength times the frequency. So remember always, the wavelength is in meters. In meters, frequency is in hertz, and this is in meters per second. All right? We're going to have an example to see how we can use this one. How we can use this equation. Now, what I wanted us to realize here is, as the wave moved from a less dense medium to a more dense medium, even though it passes through the normal, so only two things happens. The speed of the wave will change and the wavelength. Meaning, here they were longer. When you check from one wave front to the other wave front, they are longer. But once you check these other ones below here, you can see they tend to be squeezing or compressing. We can use the wave equation to explain why this happens. V is equals to F times lambda. Now, this one changes. This one remains constant. And this one does what? Changes. We can relate this one as follows. Speed is proportional to wavelength. That's the fact. Speed is proportional to wavelength. So meaning, and this one you can see they are directly proportional. Directly. So when speed increases, you can say when speed V increases, what happens to wavelength? Wavelength increases. And this is why, when you check back here, is that when we say the speed decreases, when we are moving from a less dense to a more dense medium, so you can see what is happening. The speed decreases. And according to the equation here, when the speed decreases now, this, when you say the speed decreases, so wavelength does what? Yeah, decreases. Wavelength decreases. That's it. So that's why you can see this relationship, or the behavior of the wave as it moves from less dense to more dense. We have used the wave equation to explain that. If a wave, and I'm representing this wave using wave fronts, I'm just trying to make sure that these lines are equidistant. So this is a wave moving in this direction. All right? So moving in this direction. So if we encounter a boundary here, a boundary, meaning we can say here it was in the air, and this is a glass, and our wave goes on. Now, check what happens. As the wave approaches, the very first point where it touches the glass, it will bend first. So from straight to bending, very first part that touches the line, that one will bend. So the waves inside this one will tend to be like more dense, more concentrated together. So from less dense to more dense, what happens? This one, the wavelengths are longer. So here we have longer wavelengths. Once it gets to a denser medium, this is in the less dense medium. This is quite less dense. So once it gets to glass, which is more dense, what happens again? The wavefronts do what? They squeeze in, or they tend to be concentrated together. You understand? So the wavelength becomes smaller in here, And according to the wave equation, if the wavelengths are becoming smaller, what is happening to the speed of the wave? Very good. It's also decreasing, because we said the wavelength and the speed are directly proportional. So here, yes. So here we have shorter wavelengths, and then we also have less speed. Of course, after they move out, what will happen? If they move out again, they tend to regain their original wavelengths again. So they regain the original wavelength as they were, as they move again in the air medium.